Hello, this is Mrs. Scarple with the video for topic 3.11. In this video, we've got three new trig functions. They are secant, cosecant, and cotangent. Now, while I know it might seem logical to say that secant is going to go with sine, it actually goes with cosine, and cosecant goes with sine. And what these functions are, they're the reciprocals of cosine, sine, and tangent. So when you hear or read secant, which is abbreviated SEC, it's the reciprocal of cosine, so 1 over cosine. But we have to have that description that cosine of x cannot equal 0, because now that cosine is in our denominator, it would be undefined at a value of 0. With cosecant, which gets abbreviated CSC, that's 1 over sine of x, and then again, that's when sine of x does not equal 0 to keep that from becoming undefined. And cotangent of x, which is abbreviated COT, where tangent doesn't equal 0, or might be easier to think of it as cotangent is cosine over sine instead of sine over cosine, like it is with tangent. So just flipping that around, and then you can just think about where sine of x cannot equal 0. So you'll notice that these graphs are also different because they have vertical asymptotes. We have vertical asymptotes at those values that sine and cosine and tangent can't equal 0. And if you look at it, so this first one, in the middle here, what we see is the graph of cosine. So when I hit a maximum, I'm actually going to have a concave up curve. When I'm at a minimum of my cosine, its reciprocal is going to be a concave down curve. And you'll notice that at the points where the cosine curve intersects the x-axis is where we have our vertical intercepts. Likewise with secant, if we follow the sine, where sine has a maximum, we have a concave up curve. When sine has a minimum, we're concave down. And again, at the zeros, we have the vertical asymptotes. And then we also have a range to describe for secant and cosecant, and that's because we don't have any of the values in between the maximum and the minimum of sine or cosine that are being used. Typically, the range of sine and cosine is -1 to +1, so their reciprocals are going to have the range -infinity to -1 and 1, I should say, up to +infinity. So that's going to define our range for secant and cosecant. Tangent, still going to look very similar to our tangent curve. In fact, you might even think it looks like our negative tangent curve, because now instead of starting from a low value and increasing to a high value, we're starting from a high value because we have the cosine value in the numerator down to a low value. So we're coming from +infinity and we're moving down to -infinity. And you'll also notice that it doesn't go through the origin like tangent does, and that's because that's where tangent equals 0. So you'll see that we now have zeros at pi/2 and another pi from pi/2. So pi/2, 3pi/2, 5pi/2, and so on would be the zeros, where the powers of pi become the vertical intercepts. So let's take a look at a couple of examples. I'm going to do examples 1, 2, and 3 with you before doing 2 from the last page of the notes. So here in example 1, it says let f of x equal 3 secant or 3 times secant of 2x. So what I'd like you to think of is secant is the same as 1 over cosine, so secant of 2x secant of 2x is going to equal 1 over cosine of 2x. Well, we don't want to have cosine of 2x equals 0, and normally cosine has zeros at pi over 2 and 3 pi over 2. So what I'm going to do is I'm going to set the 2x equal to pi over 2. I don't want that radian measure inside the parentheses to be equivalent to pi over 2. So if I find what value makes this expression, the 2x, equal pi over 2, I'll find a vertical asymptote. So to solve this, I would multiply both sides by 1/2. I'm multiplying by the reciprocal of the 2. And we get that x equals pi over 4. If I look at my answer choices, I see that C is a possible choice. For example 2, we've got cosecant. So think of cosecant as being cosecant of pi x is going to equal 1 over sine of pi x. And again, we don't want sine of pi x to equal 0. So to find our vertical asymptote, I'm going to find what radian measure, or think of what radian measure of sine equals 0. Well, 0 will do it, but if I set sine of pi x equal to 0, I'll end up with x equals 0, and that's not one of my choices. So my next option would be pi. So I'm going to set pi x equal to pi. And when we solve this, we get x equals 1. And x equals 1 is one of our options for a vertical asymptote. Now keep in mind with cotangent, we could add, or it'd be any multiple of, we could add any multiple of pi k to get the next one. Actually, I probably wouldn't do that in case there's some shifts and other things. So forget I was even mentioning that. We would just have to keep continuing trying some values that would potentially work. Example 3, we're looking at ranges. But in example 3, h of theta equals 3 times the cosecant of theta over 2. This 3 is important because it's telling me the amplitude. So I'm looking at the amplitude of 1 over the graph sine x. So instead of being negative infinity to negative 1, think about what 3 would do to the amplitude of sine. That would actually take us having a maximum of 3 and a minimum of negative 3. But again, cosecant doesn't use the values in between negative 3 and 3. So when I look at my options here and I know my amplitude is 3, I'm choosing option C because that amplitude has been stretched. Okay, then I said I would do some from the back. I'm going to do example 5 and then example 7. So we can solve equations that use these reciprocals or have these reciprocal values in them. In example 5, we have let f of x equal 4 cosecant of x plus 3 and g of x equals 11. In the xy plane, what are the x coordinates of the points of intersection of the graphs of f and g? For 0 is less than or equal to x is less than 2 pi. So point of intersection, they must be equal to each other. So I'm going to set for cosecant of x, oops, I almost wrote cosine, cosecant for cosecant of x plus 3 is going to equal 11. Well, we want to isolate the cosecant. So I have to subtract 3. I'm going to have 4 cosecant x equals 8. Divide both sides by 4, and I have cosecant x is equal to 2. Well, we know cosecant of x is 1 over the sine of x. So I'm going to have 1 over the sine of x is going to equal 2. Well, in the process of solving, I could think of this as being a proportion, and I could switch these two values. So I can end up with 2 equals, or 1/2, excuse me, 1/2 equals sine of x. Well, what values of x have a sine value or a sine ratio of 1/2 on the interval of 0 to 2 pi? Well, those values would be at pi over 6, and again at 5 pi over 6. So all I was doing in this process was isolating that reciprocal, changing it to writing it as the reciprocal of sine x, and then from there using the idea of proportions to help me get sine x removed from the denominator, and then thinking about what are the values of x, what are the radian measures that give me a sine value of 1/2, pi over 6 and 5 pi over 6. Our last example is going to be done in the calculator. Well, we'll have to do some calculations in our calculator, mainly because we've got all these decimals happening. So let p of x equal 3 minus 1.7 times the cotangent of 0.5x minus 1. In the xy plane, what are the x coordinates of the points where p of x equals 2, for 0 is less than or equal to x is less than 2 pi. So let's set that 3 minus 1.7 cotangent of 0.5x minus 1 equal to 2. Well, we want to isolate the cotangent. So I'm going to start by subtracting 3 from each side. That leaves me with negative 1.7 cotangent. Oops, almost wrote cosine again. Cotangent of 0.5x minus 1. To subtract 3 is going to leave negative 1 on that right side. Then I'm going to divide both sides by negative 1.7. So I'm now going to have cotangent of 0.5x minus 1 equals a negative divided by a negative is going to be positive, so 1 over 1.7. Remember that cotangent is the same as 1 over tangent. So tangent of 0.5x minus 1 is going to equal 1 over 1.7. Well, if those ratios are going to be equal, our denominators are going to have the same value, since our numerators are already equal with a value of 1. So I'm going to use that idea, that concept, that in order for these to be equal values, tangent of 0.5x minus 1 has to equal 1.7. So tangent of 0.5x minus 1 equals 1.7. Now, in order to isolate the x, we haven't really done this up to this point. In order to undo this tangent function, I'm going to have to do the inverse of it. I'm going to have to do the arctangent of both sides. When I do that, that's going to leave me with 0.5x minus 1 equal to the arctangent of 1.7. And I can find that value in my calculator. And because it's probably going to be a decimal, I'm going to wait till the very end to enter this in my calculator. I no longer need the parentheses around the 0.5x minus 1. So what I'm going to do next is I'm going to add 1 to each side, and we're going to have 0.5x equals arctangent of 1.7 plus 1, and then divide both sides by 0.5x. Oops, I don't want the 0.5 on that left side anymore. I just want the x. So what I'm going to end up entering in my calculator is the arctangent of 1.7 plus 1, that entire sum divided by 0.5. So I'm going to pull up my calculator, and I'm going to put my calculator in radian measure. I don't know that I have yet with this one. Yes, it is in radian measure. So then I'm going to just clear out of this window, and I'm going to open parentheses for my numerator. And you'll notice right above the tangent button, you have inverse or the arctangent. So we're going to go second tangent. Notice it opened up parentheses for my 1.7, so I need to be sure to close those parentheses before I add 1, and close the parentheses around the numerator value. And then we can divide by 0.5. And we have 4.078 as our approximation for x. X equals 4. I just want to pull that up again. 0.78. 4.078. So when we don't have those radian measures that we use on the unit circle, we can certainly use our calculator and get a decimal approximation. And this concludes the video for topic 3.11.